Thank you, Kevin, for the nice introduction, and thanks also to have the opportunity to be here as a speaker and talking about some of my research results which are related to AI and discrete element method modeling. And I directly today in the morning, when I started to reach this building, I was recognizing that this is the Alan Turing building. And I have it always in my lecture and always talking about 2013, when the first time the Turing test was passed by Eugen Ghostman, who was an AI who was mimicking a 14-year-old Ukrainian kid. And due to this lack and experience and his wording, he passed this AI test from Turing. Nowadays, I think the test will be passed by 70% towards an AI or a chatbot. So this method is not working anymore. But it was nice to recognize that I'm walking through this building today. So for my presentation, I have 45 minutes and I divided it in 3 parts. So the first to show again 3 examples on how to use AI or machine learning in discrete element modeling. The first one is how to use image-related AI to go into more realistic particle shapes within DEM modeling. The second part is then how to use it directly within the modeling or instead of DEM modeling, how to emulate DEM simulations and what's possible maybe also on top. And the last one is if we are finishing with our data and machine learning, then how to deal with the data, how to create models. And because of this, the name of the talk is Modeling and Simulation, with focus of advanced modeling. And for this reason, I want to start my presentation with a short evolution in the modeling. In Germany, there in Braunschweig, the most famous one in process engineering and particle technology is Hans Rum, who was a pioneer in the modeling of process engineering or processes by itself, trying to identify the mechanisms behind all these processes and the materials. And he was doing this in the 1950s, 60s, 70s. A very famous person, at least in Germany, and based on that, he tried to identify the physics behind the process on the micro scale as well as on the macro scale. And then we come a little bit further to the early 2000s, 2005 to 10. I remember the first discussions if the discrete element methodology in 2D is as good as in 3D, and then EDEM first comes up. And I remember the time when a PhD student at my institute, he was working with Itasca, and everything he does 2.5 years of his PhD was pulverized within 1 week by this new software. It was a quite impressive moment, but since that we have also doing a lot of efforts in evolving in the DEM simulations. And then maybe 10 to 15 years ago, we are starting with this, after the second AI winter at the beginning of the 2000s, we are starting again with this machine learning methods. And nowadays, we are not talking about machine learning methods anymore. We are also talking about hybrid modeling. We are talking about large language models and how to create, using these large language models, some mixture of expert systems, which is then at the end the last part of my presentation with a few slides where my vision is going within the field of particle technology. So, modeling, as I said before, is my thinking all about getting the mechanisms behind the processes in particle technology. What's behind the processes, what's the physics, and then try to put these physics in a model. Since I'm a process engineer and a traditional process engineer, this is also my mindset. And the question is now, of course, how can DEM foster this model development and identifying new physical mechanisms and the dependencies, and of course, along the process chain from the materials to the processes to the structures and material properties, application-related properties of our final product. But also, how can now AI and machine learning algorithms can help us to identify these models and help us in maybe a little bit sophisticated modeling. So my first example is on on tableting, and typically tableting is, I think, the most used solid dosage form, or the most used pharmaceutical dosage form, and it's, of course, there are existing a lot of different morphologies, particle size distributions, ingredients. There are different matrix materials with different morphologies. They have different plastic and elastic deformation behavior. And of course, you start with a solid and or a particulate system, and at the end you end up with a tablet that has zero density. And this makes it quite challenging in identifying the mechanisms behind the tableting process itself. And here the DEM simulation can help to identify the mechanisms: particle breakup, particle deformation, rearrangement of particles, and maybe, hopefully, we are sometimes able to make some kind of visual research and development of formulations in pharmaceutical engineering. So, and I will not go into the basics of DEM simulation. Hopefully, everyone here in this room knows how the DEM works. But related to this question here in tableting of particulate materials, we have typically the process where we have the dye filling. Afterwards, we have the first compression, where we have rearrangement of particles, first elastic deformation, and then at higher compression states, this is shifted to strong plastic deformation, ending up with near or full density, and then afterwards we have this relaxation and the final tablet. And especially in starting from this part to this part, we have to shift from a discrete point of view to a continuum point of view. And this makes it very challenging, especially when it comes to DEM modeling. And I would like to give a short introduction how we do it in our working group, and then switching over to how AI methods can now help us to get more information on the tableting process. So typically, if you go to the rearrangement and the first elastic deformation of these particles within the dye, this is no problem to use classical DEM. Of course, they are very plastic deformable particles. However, if you go to higher deformations, then you need to account that if you push a particle between two others, then you have a lateral expansion due to this vertical forces, and this lateral expansion leads in a very dense system to additional forces. And that means you cannot account for each single contact anymore. You need to account for one contact and the contribution of all other forces, which leads to an expansion of the particle and additional forces on top. And this is called a multi-contact DEM model, which is one part of our DEM to describe this. It's done like calculating your force as you do it normally within the DEM, and you add kind of stress tensor on top, which is coming from the stresses from the surrounding contact forces, typically by the forces of the last time step, in order to make it here computational feasibility. There's also a proportionality in between, which is given here, but then you can account for higher deformations and higher forces. On top, there's another issue. You have this very high plastic deformation, so you're starting with the rearrangement, the plastic deformation, and then the zero density of your tableting process. And due to the very plastic deformation of your typically non-spherical particles and the adhesion of the particles, you need to go for a little bit more difficult contact models like the JKR Edinburgh model to describe the particle behavior, typical the nonlinear particle behavior with the anistic deformation, the plastic deformation, and the adhesive deformation. So, and if you combine now this force model with the multi-contact model on top, accounting for all the other contacts in the system, you are then able to simulate the tableting process. Since there are a lot of particles within the tablet, several billions, which is out of computational feasibility to do it as a whole tablet. You typically go to a represented volume element and trying to define the size of the volume element that its result of a compression test give you statistical information. And if you do it with the experiments and multi-contact stress level with a prefactor of 0, that means this is just the Hertzian contact model of the classical DEM without the multi-contact model, you end up with different stress strain curves during the compression of tablets. And if you then add this multi-contact model with a certain prefactor which accounts for the stresses from the surrounding context, you are able to match your experimental compression curve to during tableting. So this is first just DEM without using any kind of AI. The question is now what's different if we are coming to very high deformation forces, and what about the better prefactor which is just fitted? So the solution is here in the first step to not account for spherical particles, to account for the real particle morphology. To account for the real particle morphology, you need a kind of a virtual particle which on average represents a medium value, or for every size fraction, your particle morphology. And you cannot just pick one from the SEM and try to put it in the DEM simulation. That doesn't work. You need the statistical distribution of your morphology characteristics within your system. And a solution for doing this, for creating this kind of artificial particles, is you can train a huge neural network, and in this case it's a convolutional neural network, where you have several particle projection areas. Every box here represents a convolutional neural network, and from each projection area you try to recreate the 3D structure for every projection area. Afterwards you use a fusion model, which is again kind of a neural network. If you have a fused system, you have then again a neural network system, which is a refiner model, and then you end up with a certain final voxel model. However, the basis of this data here is artificial, so that's no ground truth data. So this is the first issue here on the one hand, and the question is also what else. So with this AI prediction, we have some other algorithms on top, the Marching Cube algorithm to have some Boltzmann particles, Laplacian smoothing for this particles, and then we end up with an SEL file or a point cloud. In our case, we are often using the point cloud, so we then can then use this point cloud to represent it in the DEM simulation, and also we can derive all this spherical morphological characteristics like flatness, sphericity, elongation, or the aspect ratio. And this works well. So this is an original particle, this is a predicted one, and we can also take a look on some statistics, always on the original predicted one, different morphologies and the different morphologic characteristics of these particles. So, however, we have limitations, as I said before. We have, in this case, only synthetic data, and we have a bunch of projections needed for the reconstruction of this 3D particle, but at the end leads to the fact that we need the ground truth data. So that's the challenge here. The question is, can we do it a little bit more sophisticated? And one possibility is we do it as before. This is the generator I've already shown, where we have projections of our particles, and out of these projections we generate our three-dimensional particles. But on the other hand, we have also measured data, and then have a kind of GAN method, that's a combination of the generator and the discriminator, and the generator just generates new particles, and the discriminator, he takes a look on generated particles and on original particles. He compares these particles and always say, this is a fake particle or a real particle. And if the discriminator is right, then the generator needs to improve. If the discriminator is wrong, then himself needs to be improved. That means these two neural network systems improving to perfection in order to represent at the end the three-dimensional particle structure. However, we are still talking about several projections. And the question then, several projections means you need the ground truth data. Ground truth data is, for example, micro-CT data in order to describe our particle morphology and then predict our particles here, which we then may implement in the DM simulation. So, since this ground truth data is typically missing, we can also use this GAN and retrain it or restructure it in a little bit differently. So here on top, this is the GAN we have already seen, where we have here as an example 100,000 particles, where we use just 400 particles with 30 projections per particle. That means 12,000 images for training these particle structures. But we can, for the same sample, just use one projection area for example, 2,000 particles. And 2,000 particles with one projection area is something that we can measure with dynamic image analysis, for example, or via microscope. So 2,000 particles is doable with only one projection area. And the results are that you are not able to represent each particle in perfection, which is needed, which is possible if you have a lot of projection areas. But the distribution and the morphological characteristics are quite good represented. And from that, you can then use your morphological distribution to create particles which can be then implemented in the DM simulation, which is done here. We have this cellulose material, which is used for the compaction process. We made some SEM images, but what we did is also some dynamic image analysis. And from this dynamic image analysis, we get particle size distribution. We divided this particle size distribution in several classes, and for each class, we provide an average aspect ratio, and these particles in the point cloud then we implement in the DEM simulation, and then having a kind of this setup that we have the compaction process with real particle morphologies. We decided to go for bonded particles, since then we can mimic our particle properties, the plastic properties within the bonds, the plastic deformation. We don't need to go for the multi-contact model anymore. And then we are reaching during this compaction due to the deformation of the particles and the realistic representation of the plastic deformation with via these bonds a zero porosity, close to zero porosity system. Here are very strong deformations of our particles, which are not matching as perfect as before, but now we are not using a multi-contact model anymore, which has some fitting parameters. We are just having the material parameters via the cellulose within the bonds, and we have the real particle morphology in this case. So this is one example how to use AI within DEM simulations, just via representing different particle morphologies within the simulation. Nowadays, you would not do it, this is the same result here, not do it anymore via GAN methods. Typically, nowadays, we will use diffusion models, which is a little bit similar, and the way how every image nowadays is created within DALI, Stable Fusion, Midnight Journey, all these images which are created by large language models nowadays are created by diffusion models. And you can a little bit more go into the detail. You can combine diffusion models with transformer models. Transformer models are typically like GPT, like ChatGPT, which are going for writing texts. But this is just a linear sequence of different words. You can also go to a linear sequence or a surface sequence of properties of these particles. What does it mean? So surface could be handled like a language, or particle flow could be handled like a language. So there's no need to use a large language model just for generating language. You can also go for creating surfaces, and that's the reason why we are also trying to use, for example, large language models within diffusion models to create here particulate electrode structures, which can be then again introduced in the DEM simulation, and then, for example, compressed in DEM, which is especially for battery electrodes important. There's a calendaring process in order to increase the electrical capacity within the system, and yeah, this is a very nice tool to go for. So I will not go deeper into that topic. I will now switch to the second one. And the second example is on how can we use directly AI or machine learning tools within the DEM, or how could we replace DEM simulations by machine learning tools. And this is a project that starts a few years ago, and nowadays we would do it in a different way. But the idea was we are simulating a lot of represented volume elements like we have seen before for the tableting process, and having within these represented volume element around 10,000 particles, roughly. And then we are predicting from one time step to the other time step all velocities in every direction, all rotational velocities, the acceleration, the positions, and forces of each particle within this represented volume element via a huge neural network. So, and then we use this neural network, which represents the movement of particles and forces of particles, the behavior of this represented volume element in a kind of a meshed simulation, like we have in computational fluid dynamics. We're meshing our system, but instead of solving the Navier-Stokes equation, we are now solving a huge neural network, which can be quite fast solved. Which is a little bit shown here. We have different RVEs, we combine them. Of course, we need to take care on the particles which are leaving the cell, entering another one. But in the first step, you need to prove that this can be done. And we did it for several time steps, and we come to the conclusion we get a certain prediction and a certain error of our neural network system. And the more data we feed in, the smaller is the error, but still we have an error. And if you have a simulation which has several thousands or 10,000s of times, this error is stacking up. And that leads to a simulation which is not close to the DEM anymore. So the solution for that is that you're not training this represented volume element anymore. So you're simulating several time steps, like 100 or 200 time steps, and then you're using all these time steps to train the dependency of all these particle characteristic positions, velocities, accelerations on the next time step. You need a sliding window to do that within your neural network training. And then you're not training this three-dimensional cube anymore, you're training some kind of four-dimensional tesseract system. And this is an example how it works after 5,600 time steps for this compaction we had seen before of the tableting process. We have around 1,000 particles. Here are some simulation related characteristics. And here we have always the prediction with our AI emulating the DEM and the simulation with regard to the X and Z position of every particle and the stresses acting on particles. So for this represented volume element, the prediction is around 1,000 times faster for this system here. However, now we need to think about how we get this and this meshed system. That means you need a mesh, and on the other hand, you need to account for particles leaving the systems and entering the next cells. Here, did this via some overlapping meshes. which will be then fused during the processing. So we have two meshes which has a certain overlap of 20%, and then if a certain particle is leaving one cube, it's already mentioned and due to this overlap in the other one. And this is how we are dealing within the whole DEM simulation. With this is lowers, of course, the prediction effort or the computational costs of this system. This is here an example we just tried to do, since this is not a DEM simulation anymore. We needed to create our simulation setup from the scratch. That means at this point we had no geometries within our simulation. That means we mimic our geometry with particles we bond together and glue them together and then move them like a stirrer within our system. And then having particles inside the system and predicting the particle movement and compare this to the simulation, which is done here, where we have the simulation on the left side and we have this surrogate modeling on the right side. There are some slight differences here at this stage of this project, where we had here some difficulties here at the geometry of the chamber. The solution for that was to also account for a pin method just for solid or geometrical interfaces. What does this mean? We are going again to the particle level and we are predicting the movement of single particles via training the contact force model in a small and known network. However, this leads to the fact that we are going here in the area of the geometry down to a single particle level again, which of course is bad for the computational efficiency, but then we could account for having the right physical behavior of the particles, then they interact with the geometrical walls of our simulation setup. And also what we did afterwards is we were not sampling the represented volume elements anymore. You're just saying, okay, we are simulating our system, and in parallel to the simulation, we pick out random RVEs and then we use this random RVEs for training the neural network in parallel, and at a certain state we switch over and being much faster with this. But it's an example how it could be done nowadays, since I already told you that language models can be used not only for creating new texts and then language and images. You can also create surfaces or modeling the particle flow. You can deal with particle flow like a language. This should be the way if you want to do it nowadays. So this was the second example. So of course there are a lot of more examples where you can use AI in DEM simulation. Of course, we see a presentation maybe later on the use of DEM in calibration. There is a lot of efforts done in this area. This we already have seen. This was an example where we put an evolutionary algorithm within the simulation, giving the evolutionary algorithm some target values, for example, minimizing the specific energy or the wear of the system. And then this evolutionary algorithm was starting to recreate or to morph the surface of our geometry. Yeah, these were first trials here. It worked well. Now in December we get an improvement of the project for working on that further. So we will see how it works in future. But this is just during DEM simulations and on top morphing the geometry using an evolutionary algorithm. And this one here, I think this is the most easiest one, is if you do 10 simulations or 15 simulations, you get a certain kind of velocity distribution, three-dimensional in your process, in the mill or in a crystallizer, and based on this you can divide also this process in voxels and predict in every voxel the kinetic energy, the velocity, or the relative velocity between particles if we are talking about mills, like in this case. And then you can train on this voxel system with about 30,000 voxel. Again, a neural network. And you do it not only for one simulation, you do it for 10, 15 simulations, and then trying to reach all these process parameters you didn't handle in simulation. So if you have a parameter set you didn't investigate before, you try to predict it with it in the 3 dimensions, and all the 3 dimensions within these 30,000 voxels within this, using this neural network system. This is more or less a kind of intelligent interpolation, nothing more, for the 3-dimensional particle movement. However, it's quite powerful since you're saving a lot of computational power due to this method, even if it's a very simple one. So, and now I'm coming to my last step. How to use now different data to go further within data-driven modeling or hybrid modeling, and how to get now more insights on the process. So we perform several simulations, and now we need to create some models for scale-up, for material transfer, for process optimization. And the easiest way is to get out all of this data and doing some black box modeling within this data in order to predict the process. However, if you then change the material properties, if you change the process geometry or the process scale, typically this black box modeling approach doesn't work anymore. This is just a platform we built up in the past where we collect all these different machine learning black box methods. We have an automatic hybrid tuning, we have an automatic feature analysis within, we have some outlier identification, so you just upload your Excel file and then you do feature analysis, outlier analysis, you have an automatic modeling of 10 different machine learning algorithms in parallel, you're choosing the best one, and then you have on top a multi-parameter optimizer who is then doing some multi-parameter optimization. So this is doable, but this is not transferable to other scales, materials, or geometries. And the question is then, at the end, how to get the physics inside this, out of these simulations in order to be able to do this. And our approach is, in our working group, is to combine this black box methods with white box knowledge, going to a gray box approach. We are doing it using a genetic algorithm or genetic programming. In genetic programming, you represent your final equation via this syntax tree with the variables and constants at the end and the mathematical operators as nodes of this tree. And the evolutionary algorithm is then creating a lot of these trees and morphing these trees, having all this natural evolution strategies behind mutation, crossover, in order to create again and again equations which are at this state empirical, which are matching your final computational DEM results. However, typically these equations are empirical. So you get just an empirical equation if you have only a few measurement points. The most possible empirical equation is often like a Taylor row development. So you have a Taylor function with a lot of sinus, cosinus functions, which matches the data very well. So in order to overcome this, you need to put in a lot of other methods within, or adapt them on top, in order to get more physics-inspired equation. For example, a dimensional analysis, the P-bucking theory on top. Or here is a tool. I will not go deeper into every tool, but this tool here, for example, neural network, is just checking for equations. You can put equations from literature in a table, and then the system is checking the equations or parts of the equations if they are part of a solution. There are also some virtual data created, and this is also not done once. It is done 10 or 100 times in parallel, and if some equations are found again and again, the system is pushed to do with regard to this direction in further modeling. So there are a lot of different algorithms on top and things in order to put in some physics inside this modeling tool. And this is a little bit the evolution of this modeling tool from the beginning of our research until now. And we started having around 100 equations, and from these equations we produce data, we add on noise to this data, and then we try to recapture this data with this tool. So in order to mimic some data, and from the data we get the the mechanistic equations, and since we know the already existing equations, we can then judge our system, how good it works at the end. And this is a classical one, and at the end this is a latent version of this tool. It was able to find every equation out of this 105 equations. However, there's still a challenge. The bottleneck is the expert knowledge. How to get the physical knowledge from the process engineer, from the literature inside. Even you have the possibility to add equations from literature in such a table. And this brings us to the idea to couple a large language model with this software interface, that not the user is setting up the hyperparameters of each algorithm anymore, where each algorithm depends on the complexity of your data and the final equation. So this is now done by a large language model, and you get also some interaction with the large language model. Is there in the literature are there some equations describing our physical problem? And not only some real equations, but also within the contextual knowledge. Is there in the text written something which helps us to create more physics-based equation at the end? Here we are using RAG systems, where we put in all the literature we find from a certain particle question within our large language model. And then we have such a workflow where we start with our knowledge, we collect, we put that in a RAG system on top of a large language model, and then the large language model we have a conversation with, getting closer to our solution. And sometimes we already know something about the process, so we can also provide some structures, prompts. Then the large language model will have an indirect or direct configuration of this modeling software. And then at the end we have this represents the modeling software itself. Here the data set, and we get the best state set of equations. And at the end, hopefully, a good solution describing our process. Just to show this, these are some data which is coming inside. And then we have sometimes structured prompts if we already know something about our process. And at the end, we have this indirect or direct configuration. Due to the time, I would like to jump over that. If we find some equations in literature, these equations can be put in this equation library. Or we can predefine some dimensionless values or some dependencies which are added then to the data and then coming within the process. And the indirect configuration is more about creating characteristic values to describe how mechanistic is this equation afterwards. After having a final equation, judging the equation. These are both things the large language model is then doing. We tried it here on a test case where we have a DEM simulation, CFD, DEM, three-phase simulation of the droplet evaporation and the structure formation during the spray drying process. And during the spray drying process of nanoparticles, you have this segregation, which is called colloidal diffusive phoresis. There exist already some ideas in the literature, and we put our inputs in this software and the large language model, and also some ideas from the literature which were not derived by ourselves, which these here were derived by the large language model, and then trying to model our final process, which is given here. This was the original one, and we are reaching slightly increased equations. However, at the moment, we had a lot of examples where we derive a very well mechanistic equations, but also a lot of examples where it just fails. Where we're not able to derive this mechanistic equation we are aiming So and this brings me a little bit to the vision for the last 2 to 3 minutes, because in this field we are not talking about software anymore, we are talking about an agent. This agent is used by a large language model, and you can think about a modeling agent for this hybrid modeling tool, but also on the black box modeling. You can think about an agent who's setting up DEM simulations, best of his knowledge by its own, and then you can think of a kind of an innovative solution agent or expert agent within this topic, judging on this topic, and then they are collaborating with each other, and then you have the managing transformer on top. You're only working with this management transformer on top, and he is then going in a loop working with these agents, and if he gets the solution he needs, he then sends this solution back to the user. It's working like a virtual working group. This is first ideas are already published last year in other fields of research, where we have virtual working groups, which are also created by the large language model. So not in our group we are creating these agents by our own, but nowadays, since I think the middle of 2025, there's existing the Darby-Gödel machine, which is creating automatically these agents. I think this will come in the next years. This is a little bit how we do our personalized agents and what the possibilities of our agents, where we use open source models like the GPT-OSS, the DeepSeek model, Llama models. We have self-consistency algorithms on top. We can have RAG systems. You can retrain all the attention matrices within these language models to make experts out of them. And then we use these experts, combine these experts in order to solve engineering problems or to derive modeling equations. Here is an example to calculate the energy and the power input of a mill for a certain productivity, which works well with such a mixture of expert system, which is then called mixture of expert system. And you can also think about now coupling all these agents together. This is how it looks with our online, where we have here the language model we can interact. We have the language model training, we have our database, we have a mixture of experts set up where we can combine every language model, every expert with everyone else in order to set up some virtual working groups. So I will jump over this because of lack of time. And the hybrid modeling framework is then just one agent. This other framework here I have shown before, which is called here Particle OS. It's just another agent. Here's a DeepSeek behind at this point. And the DeepSeek can perform all these tasks. So normally this is a video here. There's analyzing a request and then doing all these things by its own. Also we connected the large language model also to PyFluent, and PyFluent was then controlling Fluent. And you just prompting that you need a simulation of a reactor, the shear rate distribution in a reactor, and then system asks for which reactor, you upload a CRD file. When he asks for material properties, filling degrees and rotational speeds, you provide it, and then he opens Fluent, he doing the meshing, importing the geometry, doing the simulation, and giving back the final result, which is working for easy cases, not for complex ones. And with this, I'm at the end of my presentation. I would, of course, thank all these funding agencies and you for your attention.
Hi, Dennis, for questions. Carsten, you said that you'll be around for the rest of today, but you'll not be here tomorrow. So we do have obviously tea and coffee breaks. We'll have dinner this evening, so you'll have plenty of time to catch Carsten and ask some questions if you don't have a chance in the next 5 minutes. So do we have any questions?
Very nice talk. It's quite interesting where you're pointing to where it's maybe going with this agentic workflow, but the thought that comes to mind when you mention that is, are we almost not back in the same problem when we are where we are at simulations in industry at the moment where it requires expert knowledge to define DM simulation, you still have to have the expert knowledge to define the prompt for the AI. And if you don't know that you need a cohesive DM simulation, you won't know what to tell the AI model to do. So it's almost like we're just coming back to the problem that we kind of glossed over all along, that how to go about defining our models more rigorously and documenting it more rigorously, so that that expert knowledge that input bit is maybe where we're going to fall down on all of them, whether it's DM, NPM, AI.
Yeah, I run over that a little bit. So typically, if you ask GPT about the population in Northern America, it will give you a certain answer. If you're digging deeper and deeper, then you see, okay, the expert knowledge is maybe missing. Maybe it's not missing during the training process, but you have such a large monolithic system that it has, it's more a generalist, like an expert. But what you can do, and but what is already shown in literature, and also we have shown it in our research, you can train a very small Llama 2 system. You have only 7 billion parameters instead of 400 billion parameters. It can be done by a lab. And just feeding in all literature on particle technology, just to retrain the probabilities within the attention matrix. The system has afterwards nothing to do anymore with the population within Northern America. It just knows something about particle technology. Everything else is then deleted. But then you have much deeper insight and you get better answers out of the system. And this is one opportunity to do it. And if you think it a little bit further, we just did it with a few books. If you put in all the literature from all over the world just to retrain a larger system, which is a real expert in particle technology, I will not believe that I could give better answers, since I don't know every literature in the whole world. So maybe could do my job better than I do. The experience, that means the experience is there.
We want to train the AI to be prompting us with the questions rather than us telling it what we think we want. It's almost flipping it around the other way. It's read everything we've read 5 papers. So maybe it should be asking us the questions what we want rather than us telling it.
You need this interaction, of course. This management transformer is needed. You need this interaction. You need precisely say what you want. And this is something, also the reason why a lot of people need to learn prompt engineering, and that's the reason why we get bad results from the large language models, if they do a bad prompt. And you can use so large prompts that you get a very precise answer, and the reason how to get it, how to come to this point.
Any other questions? Stefan?
Excellent talk. Really enjoyed it. Very relevant things. Following up on the point, I mean, one challenge I've seen is, you have this wealth of literature, but how do you force it to consider thoroughly the literature? What we find is that there's memory limitations, so time, speed limitations, and so it tends to converge to the first answer that it sees. So if you have 100 papers, different perspectives, you'll find the first 3 and synthesize an answer, plus you might hallucinate a little bit. But have you solved that problem of getting it to thoroughly consider a large amount of data, amount of literature?
That's an interesting question. That's typically the case if you're using RAG systems. You're putting your publications in a database, making a pointer database, a vector database out of this, and then the large language model is searching within this database. But the embedding strategy is to retrain the whole system, that all the whole attention matrix is retrained. And the best results you get if you use both in parallel. If you combine it, and due to this retraining, you get a different answer than just searching paper by paper. This is a totally different procedure. Again, this is one thing, and the other answer I already forgot. In our case, we have a kind of self-consistency improvement afterwards. I just told about that. It's like you're asking the system 10 times the same question. And if you get 10 times the exact same answer, it has knowledge of the system. If you always get a different answer, then the system don't know. and then it's visioning at the end. But also visioning is a very interesting part. If you have a lot of visioning, maybe you can combine visioning again with evolutional algorithms in order to create creativity, maybe. So this is the reason why our language models are able to, can be adjusted within the temperature. That means 0 temperature means totally consistent, and 100% temperature means it can vision a little bit, and we can adapt this via just smoothing it and say, you need to give us the best answer on.
Fantastic. So in the interest of time, we'll have to leave it there. Thank you very much, Carsten. And again, during the coffee break, feel free to catch Carsten, who will answer the rest of your questions.